Hi there, and welcome to Grocket.com. This is the GRE video, beginning of the video series on the GRE quantitative test, the math side of the regular GRE exam. And my name's Jim Jacobson. Did I say that already? I've been doing test prep for about 10 years now, helping people get better scores and showing them tips, tricks, strategies. And so that's what I'm going to be doing with you today. Hopefully, no, not hopefully, with practice, and there will be practice. There is homework for you to do after this lesson. With practice, you can incorporate these strategies and this information into your test-taking approach and get a higher score, having a better opportunity to show what you really know and what you're capable of to graduate schools, so that when you apply, they look at your score and say, thumbs up. All right. So let's get started. So today we're going to talk about the intro to the quantitative strategies, kind of an intro to the quantitative section overall, as well as talk about number properties, one of the key elements to kind of basis of the quantitative section. We do get to bigger topics later. You can't avoid doing algebra and stuff like that, but we do need to talk about number properties first because that underlies all of these things. So, in case you didn't believe me, so like I said, today, intro to the quantitative strategies and number properties. Then we start getting into word problems, which can be anything from geometry to algebra to statistics to whatever. Equations and coordinate geometry, the types of things that you are likely to see the most often. We gradually move into things that are, that you'll see in smaller percentages on the test, but you really are still expected to know. So we'll cover averages and percentages, rates, inequalities, absolute value. 2 lessons on geometry, because for most people it's actually been a while since they've done any geometry. If that's not you, I guess you don't have to listen to my videos. It's up to you. We may still be able to give you useful information, but for a lot of people, geometry was like sophomore year of high school. So if you haven't done this stuff in a while, it may take a bit to shake the rust off, which is why we're covering it in more detail. Also, standardized tests love the geometry stuff, so because it's a very discrete, with an ETE set of information, and they can come up with a lot of creative problems using that same small set of rules and formulas that you can be expected to know on test day. And then we'll cover the data analysis and statistics and probability. Data analysis, of course, is not escapable. Statistics and probability are higher end questions, so it's possible you wouldn't see one. But on the assumption that you're interested in a good score, why would you be watching this if you weren't interested in a good score? We need to cover that topic. So without further ado, let's get into those quantitative strategies. So 4 question types on the test, and some of these are newer than others. Multiple choice, select one answer. Since the dawn of time, mankind has been answering multiple choice questions, and these are like those ones that you've seen before. Multiple choice, where you have to select one or more answer, are a little bit different. You may not have done one like this before. In this case, one answer may be correct, but it also may be more than one, and you have to select. They may ask you to select 3, or they may ask you to select all that apply. So, be aware that it won't just be choose one of 5, that there may be a more complicated approach that's required. Numeric entry is new. It requires you actually to enter a number, hence the name numeric entry. And these ones can ask you for more complicated decimals, things like that, because you do have the use of a calculator on the exam. Finally, quantitative comparisons, and we'll show you what these look like. You're comparing 2 quantities, hence the name, and you're trying to decide which one is greater. They will usually not just give you a number like which is greater, 2 or 3. There will be something algebraic or some element of geometric, some problem that you have to solve in order to solve that one. And there's 2 ways that these questions can appear. One is that they appear kind of absolutely as an individual question. The other is that it'll appear as part of a series of questions on data interpretation, where you're given a body of information and then asked to answer several questions on it. It's rather like a math version of reading comprehension in that way, that you'll have, a set of stuff. I'll show you what that looks like too. Let's take a look at some samples, because that's what I said we were going to do. So here's a sample question of a multiple choice with one answer. So, we have if c plus a equals 20 and b minus c equals 8, then a plus b equals what? And there's several different strategies that you can adopt, and we'll talk about those later. But in this case, in any case of a question like this, only one answer is correct. You can use process of elimination or plugging things back into the question, but only one of these is right. If you're able to eliminate, for example, 2 of the 3 by some other means, you get your odds of guessing down to 50%. A 50% chance of getting it right, even if you don't know whether it's which of these 2 it is. And this is a problem from the Grocket vaults, so you may see the problem again in your practice. Okay. So when you have those single answer questions, where you only have to select one answer, one right answer, we have a couple strategies that we want to give you. One is plugging numbers in. So of course, your number one strategy, your number one best way of solving any problem is to just know how to do it. Know the answer. So if you know how to do something algebraically, that's almost always going to be faster than either of these strategies that we're giving you here. Not always, but usually. And so if you can do it the quote-unquote right way, that's great. If you can't, excuse me, if you can't do that, getting the right answer is still the way to go, so we have a couple of the strategies that can help you. First one, plugging things in. So if you have word problems with variables, and then numbers in the answer choices, in particular, that's a good candidate for taking things and plugging them back into the original problem. I'll show you how that works. So we'll cover algebra in a couple sessions, but plugging things in, we would just try an answer. We want to start with either B or D. I'll show you why. Let's start with answer choice B here. No, let's start with D. No, we'll start with B. Okay, anyway, it doesn't matter. You won't always know which one is good. We'll start with B. So you just plug this in. So 1/3 of 1 plus, and we take this value in answer choice B, plug it in for x. And we set it as equal, even though we know that it may well not be. What we're doing here is trying to zero in on the right answer. So we figure out, well, 1/3 of 1 2/3, 3, 4, 5. So this is 5/3. So 1/3 times 5/3. Well, 1/3 of 5/3 is not 3. It's actually 5/9, which is a little bit less, or excuse me, a little bit more than 1/2. So it's not even close to 3. So the reason why you start with B or D is because if you can tell, and you won't always be able to, but if you can tell whether the answer that you have is too big or too small, you can go in either direction. If you know for a fact that your answer was too big, and you started with B, A has to be the right answer. So that's really great. If it's not, then you know you have to go in the other direction. You make D your second one. If D is the right answer, you're in good shape. If not, if you need to go lower, it has to be C, and if you have to go higher, it has to be E. So it's pretty great. There will be some problems where, because of the way the problem is worded, you won't always be able to tell whether your number is too high or too low, and in those cases you'll probably have to try just all the answer choices until you get the right one. That's the price you pay, and that's why I say that knowing the answer is still the best approach, but if you can't, plugging things in is pretty great. Just to show you the rest, we tried D here, so 1/3 of 1 plus 3 equals 3. So 1/3 of 4 equals 3. No, actually it does not equal 3, it equals 3/4. Or excuse me, 4/3. 4/3. 4/3 is 1 1/3, which is still less than half of the number that we're after, which is 3, so we have to go still higher. It has to be E, but just for the sake of illustration, I'll show you how that would work. So 1/3 of 1 plus 8, using this value in here, equals 3. Well, sure enough, this ends up being 1/3 of 9. 1/3 of 9 is 3. So that's how that works. Can get you a lot of points on test day. So just practice this strategy. Whenever you're feeling a little bit lost and you have numbers in the answer choices, try plugging them back into the original question. I mean, it can't hurt, right? It may get you more points. So the other strategy here is using numbers. So you don't have to do every problem algebraically. Sometimes you can actually just magic up some numbers that work for the problem. And sometimes there's really good ones to choose where it really is easier to do it this way. So an example here, when you have a percentage problem in particular, or variables in the answer choices and in the original problem, picking numbers for them can make a big difference. With percentages, your buddy, your best friend ever, your BFF number is 100. Okay, because the first increase or decrease on 100, if you have to do a 50% increase on 100, the new number is 150. That's why you start with 100, because the first increase is done for you, basically. So our example here, Jessica's sales increased by 20% from 1997 to 98, and by 15% from 1998 to 1999. By what total percent did her sales increase from 1997 to 1999? Now the trick here, of course, is that her sales went up and then they went up on top of that. So, the amount of increase in the sales from the two time periods, we can't just add 20 and 15 because the 15% increase is done after that first 20% increase has happened. It's not on the original number. So we can't just add these two together and say 35. So this is the one answer we know it isn't. And in fact, if we wanted to logic our way the rest of the way, we could say, well, if it increased 20% and then increased 15% on top of that, it can't be this and it can't be this because it went 20% in the first year. Since both of these were positive increases and this one was the simple sum, it has to be this one. Now let's just say it wasn't that obvious. Let's say we just had to actually pick a number. We pick 100. So in 1997, she's at 100. In 1998, she has a 20% increase. She's now at 120. See how easy that is? You start with 100, and whatever the percent increase is, you just add that on to 100. That's the new number. If it's negative, you subtract it. The trick, of course, well, it's not really the trick, but the problem is we actually have to do a little bit of math, because then from 1998 to 1999, she went up 15%. Now, I'm lazy about math, to tell you the truth. I mean, yes, you have a calculator. Sometimes it's faster to do things in your head, though, than to actually sit there like punching a bunch of numbers in. In this case, it's easier to say, well, since it's a 15% increase, 10% of 120, you can just move the decimal point over 1. That's how I figure out the tip in the restaurant. I know, go me. So you move the decimal point over 1, 10% of 120 is 12. 15% will be another half of 12, which is, so 15% of 120 is 12. The additional 5%, 10% is 12. The additional 5% is 6 for a total of 18. We add 18 onto 120. And we're at 138 in 1999. 138 is a 38% increase over 100. Again, the problem could be much more complicated than that, and 100 could still be the right answer because it makes the math that much easier. So with one answer strategies, you need to be aware of easy answers, especially in difficult sections. As you've been getting a bunch right, the questions get harder. So the further along you've gone, the more likely it is that easy looking thing is probably not the right one. Also be aware not answering the question asked. So the easy answer in the one we just looked at was that 35%, or 20 or 15, which were also just numbers right from the problem. Also be aware not answering the questions asked. That could be a problem too. So the figure to the left shows two concentric circles. The 9-inch diameter of this guy is equal to the 9-inch radius of this guy. And so as you may remember, and as we will cover when we get to that geometry, the area of a circle is pi times the radius squared. So to find out the area of the donut without the hole, we subtract the whole circle, the area of this whole thing, minus the area of the donut hole. That will equal the area of the donut itself. So it's actually going to be the area of one circle minus the area of the other circle. We subtract the little one from the big one. The big one is going to be pi times its radius squared, so pi times 9 squared. This one is going to have a radius of 4.5. I'll put that in blue so you can read it. The radius is going to be 4.5 here because the diameter is 9. So pi times 4.5 squared. Anyway, we go the rest of the way through this one. 4.5, notice all these are in fractions, so we probably want that as 9 halves. So let's put that down here. So we have 81 pi minus 81 fourths pi. And if we convert 81 into fourths, and so here's where you could use your calculator. You can either subtract it and then convert it into fourths, or convert it into fourths and then subtract it. We'll get into the geometry later, and so I don't really want to get into this in too much detail now. But you end up with, 81 pi minus 20 1/4 pi. You end up with 60 3/4 pi, which isn't in your answer choices, but 243 over 4 pi, which is what this is in the answer choices. Note that we have the 9 halves, which is what the radius was, but that's only one of the circles. 243 over 4 is almost the right answer, but it's missing pi. So you can see how they'll give you answer choices that are suspiciously like what you need. So if you're careless, if you forget to include pi in a circle question, for example, they may get you with one of the answer choices without pi. So, be careful. Don't be that person. So this is the one that I alluded to earlier, the type of question that's new on the GRE, where it's multiple choice, where one or more answers will actually be correct, and they'll specify whether you have to select a certain number or whether it's open-ended. So, for example, here's one from our GRE database. Which of the 3 following integers have a product that is less than -85? So it will actually be 3 of the answer choices, 3 of the 6 in this case. So selecting only 2 or more than 2 will not be sufficient. There is only one correct answer, even though we need to select 3 of the numbers. They won't always specify the number. It may be, select select all that apply, as you may have done in surveys. So pay very close attention to the format, because otherwise you'll get it wrong, and you don't want to do that. So your strategy with the 1 or more answers, definitely understand how many answer choices you have been asked to fill in. Write it down if you need to. Keep it straight. Chant it to yourself. No, don't chant it to yourself. But, stroke your chin the number of times equal to the number of answers you have to select. If it's open-ended, you just keep stroking your chin the whole time. I'm joking, of course. Realistically, though, it could be, because it's the type of careless mistake that someone might make under pressure, they're counting on some people making it. So don't be that person. A statistically significant number of people have to make a mistake on all sorts of problems on the test in order for it to be useful to college admissions. So don't be the one making that mistake. So make sure you do that right. When you're eliminating, find the upper and lower bounds. So some types of questions will give you a range of numbers, in particular inequalities and absolute values. You can use that to your advantage. You'll be able to tell sometimes that certain answer choices are just not going to be possible. So, if you can tell from the problem that the biggest answer can be 8, then the answer that says that the answer choice that's 9 or 10 is automatically wrong without you even having to test it. So look for little tricks like that. And then again, recognizing that overall predictability of math, the rules are pretty set. They're not inventing a new, the style doesn't change for how we compute the area of a circle. The equation of a line also doesn't change. So getting comfortable with the patterns that develop in sequences and sets and formulas can really make your life easier. If you are the sort of person who gets anxious about math, doing a lot of practice can help alleviate that anxiety, especially if you do targeted practice at your actual level of ability, as opposed to shooting too high and getting frustrated. So getting used to the predictability of math can really make your life better, or at least your GRE testing life better. So numeric entry was the other one that I mentioned, the kind where you actually have to enter in an exact number, and you can have 2 different formats in this case. Both of these are from the GRE database. So the first one, an insect colony doubles in population every 10 years, so doubles every 10. Its population is reduced by 20% every 7 years. After 50 years, the population of this colony is how many times its initial population rounded to the nearest integer. So note that we've been given some specific instructions about how to round, and then we actually have to enter in a particular answer. So even if the real answer is 4.7, we need to round that to 5. If the real answer is 10.3, we need to round that to 10, nearest integer. This is to be contrasted with the kind that we have down here. Charlie and Lucy are painting an office. Working alone, Charlie can paint the room in 6 hours, and Lucy can finish the job in 4 hours. How long will it take them to finish? In hours, if they work together at their respective individual rates. Express your answer as an improper fraction. So in this particular case, it needs to be an improper fraction, which will mean the numerator is larger than the denominator. So there'll be a big number up here and a small number down here. What you can't do is put a decimal in one of these 2 slots. You can't put 3/4 or 4/3 up in the numerator and leave this blank. You have to put the 4 on the top and the 3 on the bottom. So that's what those will look like, and they can appear in a variety of question types. So with numeric entry questions, absolutely, and make sure you're answering the right question, because unlike multiple choice answer choice ones, there's no kind of guidance there. With multiple choice, if your answer is way different from the multiple answer choices, you did it wrong. Since you're just entering in a number, you don't have that guidance from the answers, so you need to be really sure you're answering what you were asked. and then the way that you're asked the format that the answer's in matters. Whether they ask you for a decimal, an integer, or a fraction. Definitely round your answer to the nearest figure that you're asked. Remember that, with decimals, it's tenths, hundredths, thousandths, 10,000ths, and the powers of 10 to the right of the decimal point, even though it's units and then tens and then hundredths on the left. Rounding, you do not round until the end. So if the question asks you to round your answer, you do not round until the final answer. You leave all of the other answers, messy decimals and fractions and stuff, you leave those unrounded until the end. On multiple choice ones, you can round along the way if the answer choices are far apart, because the answer choices are far apart, and whichever one you're closest to is likely to be the right answer. On numeric entry ones, do not round until the end, if even then. Sometimes they will still insist that you put a decimal in. And then finally, be familiar with how you're asked to do this. You have to put in the metric, each of the blanks separately, and this is particularly important because their little calculator that they have has a transfer button on it, so you can take a number, like a whole decimal that appears in your calculator, and transfer it to a blank, but that's really only going to work if you put it in the right blank. And if you have one like the one we had before where there's two blanks, that transfer thing is going to be trouble. So just be warned, practice it in a place that gives you online tools similar to the one on the test, just to make sure you get it right. So then quantitative comparisons is the fourth of our major question types. You may have seen this in previous versions of the GRE if you've taken it before. Basically, you have two quantities and you are asked to compare them. You'll get column A and column B. The answers are the same every time. The right answer is not the same every time. It's not like it's C every time. But the answer choices, that A is that the column and quantity in column A is greater is always choice A. B is greater is always choice C. The fact that they're the same is C, and that you can't tell from the information given is always D. So you'll have this memorized if you've done this right, because you'll have done enough practice problems that you're like, yeah, you're saying the quantitative answer choices in your sleep, or quantitative comparison answer choices anyway. So this one has some common information in the middle, and then that applies to both columns, and we have to do a little figuring before that. Sometimes there will be no common information, and you just have to compute something that's in column A and then compute something that's in column B and figure out which is greater. So we'll cover more information on that later, but just know that it can vary a little bit in format. So your strategy overall, like I said, answer choices are always the same. You don't need to do all the math. You just need to do enough that you can actually compare the two columns. And this is an important distinction to make. Sometimes you will actually have to do all the math. But if you already know that column A is bigger, don't finish the computation the rest of the way. That's time that you can devote to getting another question right elsewhere on the exam. So that can really make your life easier. So just recognize when it's time to stop. And for shapes, note if the figures are drawn to scale. If they are drawn to scale, you can use that to your advantage by eyeballing some of the figures and try and figure out which one is plausibly bigger. Now, they're usually not going to make it something super obvious visually, but you can at least determine whether your answer choices are plausible based on the information you're given. If the figures aren't drawn to scale, just pretend that you know the figure is a liar in some way, because it might be. So if it's not drawn to scale, don't use it for anything other than telling that it's... You can only use the information that you're definitely given. We'll talk about that more later. And then if you're unsure, test with the sort of things that break given statements. So negatives, positives, fractions, 0, and 2, if it's a question about primes, are all things that can kind of be exceptions to the rules. And if you're trying to determine whether column A or column B is always greater than the other one, testing the exceptions helps you make sure. There could be cases where, because of these exceptions, the answer choice will be D, that it cannot be determined. So sample data interpretation is that final... It's not really a question type, it's more of a question format, because you're asked the same types of questions. You'll either have multiple choice answer 1, like this, or it'll be numeric entry, which we've already talked about. In this case, though, you're given information on a graph, and you'll note that there's all sorts of stuff. These are, two different... We have different bars for males and females in different departments, and these are percents of these total numbers here. And then we're given additional information in the problems themselves. So there's a lot to comprehend, and it's in your best interest to get a sense of what's on there first, before you start tackling questions. So your strategy is, of course, number one, get a broad feel for the graph and chart, look at the axes. What is it actually saying? What are the trends, if any? It's kind of like reading comprehension. I think I mentioned that already, in that you have to do a little bit of there's an initial time investment here where you have to kind of understand what's going on before you can tackle those questions. So titles, units, labels, captions, all that stuff, they could test you on anything they give you. You can eyeball graphs. They are drawn to scale, so you can tell whether an answer is just totally implausible sometimes, and then you can just eliminate it. Or you can tell whether the answer you got is wrong, and then that tells you to either start over or guess and move on, depending on how you're doing on time. And then finally, all the information you need in front of you is going to be in front of you. The previous one was about doctors working in different specialties. You don't have to be a doctor. And in fact, if you're studying for the GRE, you probably aren't one. But so you don't need to know anything about the topic. Everything you need will be given to you. And so what you're expected to do is a variety of things. Sometimes you'll be asked to just interpret what's on the graph. What were Division 3 sales in the third quarter? You have to correctly identify Division 3 out of multiple divisions, presumably, and correctly identify the third quarter ones. People can mess this up. It's easy to make a careless mistake, especially when you have a lot of information that's close together on a graph, like a lot of bars that are tiny and small and next to each other. Sometimes you'll be asked to manipulate the information on the graph. So you may be asked to do something about Division 3's sales in the third quarter, like compare it, or is half of Division 3's sales in the third quarter less than a quarter of Division 4's in the fourth? Where you'll have to do something with it. Sometimes there will be approximation and rounding. Look for words like approximately to be your clue. This is actually true of the quantitative test in general. Just know that sometimes you aren't going to be dealing with the exact numbers. And finally, like reading comp, and I've made this connection a couple times now, sometimes the answer comes from more than one place within the information you're given. So just like the answer to a reading comp might be in more than one place in the passage, like part of the answer might be in paragraph 1, part of it might be in paragraph 4. With these guys, part of it might be in the graph, and part of it might be in a chart or a table that came with it. So just be prepared to not have everything in one place, that you'll have to make connections and transfer information from one part of your data set to another. So now we're getting into arithmetic, those building blocks upon which algebra, geometry, and other fun stuff will be built in the course of this video series. Factors, multiples, and divisors. First off, some basic terminology we need to cover. An integer is a whole number, so a positive and negative whole number. So numbers like, actually I'll bring that up there. Examples include -3, 2, 0. So the numbers the markings on the number line on either side of 0 and including 0. Not examples would be things that are not whole numbers. -3.5, 2 and 1/4, the square root of 2, things like that, not integers. So guys like this, not like this. A prime number is divisible only by 1 and itself. So then that's the dictionary definition. And so they're always positive. They're always whole natural numbers. So they look like integers, but of course they're never negative. So they have two factors, okay, 1 and itself. So a prime number, for example, would be 3. The only two different numbers that you can multiply together to get 3 are 1 and 3. 1 times 3 equals 3. That's how you define a prime number. So a number like 6, which you could do 1 and 6 or 2 and 3, is not prime because there's 4 factors. Factors are the numbers that you can multiply together to get a bigger number. A number is always its own factor, as is 1. But primed are the ones that have only those two. So important questions. Are there any even prime numbers? Are there any numbers that are even that you can only divide by themselves in 1? I'll just answer that question for you. Yes, and standardized tests love the number 2. Remember, you can only multiply 1 times 2 to get 2 in terms of two different factors. So definitely an even prime number. Is 1 prime? Now, if you've been following along, our definition of prime is that the number has to have two factors, two different factors. How many numbers can you multiply together to get 1? Only 1, which is 1. 1 times 1 is 1. So 1 is in its own special case. It's called an identity, or you could just call it not prime like the rest of all the other numbers. But basically 1 only has one factor, which is itself. Is 1 prime? No. Is 0 prime? No. 0 is prime for the opposite reason. Since you can multiply any numbers together with 0 to get 0, there's no, 0 is also not prime. You need to have 2 and only 2 distinct factors for 0, whereas 0 could be 0 and 1 or 0 and 11 billion. Are there any negative prime numbers? No. Remember, part of our definition is that they're positive. Even a number like -3, you can multiply 1 times -3 equals -3, or -1 times 3 equals 3. So if you want to even introduce the idea of being able to multiply other things together to give you -3, it still has more than 2 factors. So no, there are no negative prime numbers. Okay. So here's an example of a number properties problem from the GRE vaults. Which of the following integers cannot possibly be the sum of 2 prime numbers? Select all that apply. So this is a select one or more answer choice question. And so there's going to be at least one, and it could be all of them, in theory. So we already established from the previous page that a negative number can't be prime. And the only way you can get a negative number by adding things together is if you're adding together negative numbers at least once. So like you could have 4 plus -7 equals -3. But in that case, this can't be prime and this isn't prime. You can't even do 1 plus, or 2 plus -5. Because even though 5 is prime, -5 is not. So can't be this one. This one cannot be the sum of 2 prime numbers. So that's one of our correct answers. What about 3? What numbers can we add together to get 3? We can add 1 plus 2, but remember 1's not prime. We can add 3 plus 0, but remember 0's not prime. So this actually is another one of our options. We could add 1.5 and 1.5, but those are also not prime because prime don't have decimals or fractions. So 3 is also a number that cannot be the sum of 2 prime numbers, and therefore it's one of our answers. What about 8? Well, 8, it could be 3 plus 5. 3 and 5 are both prime numbers. It may help you when you have a prime question, if you're not as comfortable with primes, to memorize the first few prime numbers and then write them down. So the first few prime numbers, 2, 3, 5, 7, not 9, because 9 could also be 3 times 3. If it were only 1 times 9, it would be prime. But since 3 times 3 is another way to get 9, it's not prime. However, 11 is prime, 13 is prime, 15 isn't. All the rest of these are odd except for the first one. But 13 isn't, or 13 is, 15 isn't, 17 is, and so is 19. Anyway, there's more of them. You know, in fact, nobody even knows how many there are. In theory, they're infinite. But knowing these first few, especially the ones up to 10 or 11, really make your life easier. So 8 could be 3 plus 5, 2 numbers on our list. D, can we get 2 numbers on our list to be 9? Well, 7 plus 2, that's 9. 7 plus 2 equals 9, 3 plus 5 equals 8. So since it can be the sum of 2 prime numbers, it can't be the right answer. We need the ones that cannot possibly. You know, we could do it so that it's 2 not prime numbers, 1 and 7, but it still could be this other one. Or sorry, like 5 and 4. That would be a naughty one. Anyway, so not C, not D. 18, well, we could do 5 and 13. 2 more prime numbers, and since we were able to come up with a way for 2 primes, it's also not the right answer, leaving us only with A and B. Some other number properties to talk about. Negative times negative is always positive. Just remember it, it always is. Positive times positive is also always positive. It's only when you have a negative times a positive that you end up with a negative number. So memorize these if you have any spare brain space. These are absolutely mission critical to getting so many questions right on the test, on the quantitative side anyway. So negative times negative, positive times positive, both give you positive. Only negative times positive gives you negative. putting that into practice. So which of the three, and we actually did this, we had this as an example of a choose one or more answer choice when we were doing our sample problems. Which three of the following integers have a product that is less than negative 85? So remember, less than negative 85 means more negative. Like if you have negative $85, that's more money than negative $185. They're both not good amounts of money to have. But negative 85 is smaller, or excuse me, greater than something that's more negative. Anyway, so we need a big negative number. How can we get a big negative number? And we have to do it with three numbers. So knowing what we just learned about positives and negatives, to get a negative number at the end out of three numbers, we either have to have positive times negative, or we need to have negative times negative times negative. Anything else will give us a positive number. If we do plus plus plus, that's positive. Also, if we do minus minus plus, two negative numbers, these two, negative times negative is positive, and I could turn that into a smiley face, I guess, turns into a positive number. So it has to be one of these two. Now there's only two positive numbers in our list, so let's try this out first. So this would be 7 times 2, and then we need a negative number. We're trying to make it as big as possible. We're trying to make the number part of it big because it has to be more negative than negative 85. So our biggest one is negative 6. So 7 times negative 6 is negative 42 times 2 equals negative 84. Just a bit shy. Negative 84 is actually greater than negative 85 because it's less negative. Anyway, we need something like negative 86. So it's not positive, positive, negative. The only other option then is negative, negative, negative. We can get rid of these two answer choices just by doing that. And now again, we still want as big a number as possible, so we choose our three biggest ones, 6, 5, and 4. Negative 6, negative 5, negative 4. Negative 5 times negative 4 becomes positive 20, but positive 20 times negative 6 becomes negative 120, which fits the bill of being less than negative 5. So it is these three. Evens and odds, another set of things that really you do need to memorize. I mean, I'm sorry to tell you that. Nobody likes to hear that they have to memorize this in addition to learning words and grammar and stuff. But, your ability to prepare for this test is one of the things that graduate schools are testing. So commit to memory the following. Even times even is always even. Even times odd is also always even. It's only odd times odd that always gives you an odd number. If ever you're not sure about these rules, you just, whatever reason, just pick numbers like 2 and 3 and test them out. So even times even would be 2 times 2 equals 4. Yeah, it stayed even. Even times odd, 2 times 3 equals 6, stays even. Whereas 3 times 3 equals 9, it stayed odd. When you do even plus or minus even, so let's say 4 plus or minus 2, 4 plus 2 is 6. 4 minus 2 is 2, so even plus or minus even stays even. Even plus or minus odd, so let's do 4 plus or minus 3. So it's either 7 or 1, both odd. So this one is odd. Odd plus or minus odd. Again, let's do 5 plus or minus 3. We get 8 or 2. So odd plus or minus odd is even. Again, whichever is easier, I guess. Either memorizing these rules or being very comfortable just reinventing them, re-engineering them, rederiving them on the spot if you have a problem that involves these things. So, but I think they're worth being very comfortable with no matter how you do it. Properties of 0. Is 0 positive or negative? Neither. If you look at a number line, pretend that's a line, 1's here, negative 1's here. All the negative numbers start at 0 and move that way. All the positive numbers start at 0 and go that way, but neither of those includes 0. 0 is neither positive or negative. It is neutral in all disputes of the cosmic struggle between positivity and negativity. Is it odd or even? Now this one, it does actually have a value. Because it is one of these even, I gave it away there, because it's one of the intervals on the number line, so like here we would have negative 2 and here we'd have positive 2, so this is an even number, an odd number. This must be an even number because we alternate between evens and odds on the number line, even odd, even odd. So because 2 and negative 2 are even, and then you have odds before it, 0 is considered an even number. 0 times any number is going to stay 0, whereas 0 plus any number will stay that number. So 0 times x gives you 0, but 0 plus x gives you x. Any number divided by 0 is undefined. If you think about it, you can put an infinite number of zeros into something because you're putting nothing in. You can do that as much as you want and it doesn't change the value. So if you have a savings account with $100 in it, you can make $0 deposits all day for the rest of your life and you'll still have $100. But it's undefined how many times you could really do that. So maybe that doesn't help you remember it. But just dividing by 0 is naughty. Maybe it helps if I just write that. Dividing by 0 is naughty. The GRE will not do that and will go out of its way to avoid it. I'll show you what I mean. All right. So the order of operation, PEMDAS, if you can't remember PEMDAS, there's a mnemonic device. Please excuse my dear Aunt Sally. You can come up with something funnier or naughtier if you want, as long as you remember it on test day and actually while you're doing your homework. This represents the order that you should do things. If you don't do operations, a complex thing like this guy here, if you don't do it in this order, you will get a different number, and that number will be wrong. So the GRE is expecting you to have this internalized, memorized. On test day, you do parentheses. Anything that's in parentheses you do first. Then you do exponents. Then you do multiplication and division in that order from left to right. Technically, they can be done in any order. They're whatever that property is, commutative or something like that. But if you want to be consistent, make sure you don't miss things from left to right in that order. Same thing with addition and subtraction. They can, you can do them individually, but it is best to do it just from left to right to keep yourself straight. So do it in this order, otherwise bad things happen. So we would do the stuff in the parentheses here first. So this just becomes 5x quantity squared. Then we would do the exponents. 5x quantity squared becomes 25x squared. And then we would have 2 times 25x squared plus 6x minus 3 all over 3. Then we'd go from left to right, do the multiplication. This then becomes 50x squared. And then we have like this factory thing that we might have to deal with. Anyway, that's how that works. Memorize that. Sorry to keep telling, not everything that I'm going to be telling you is memorized stuff, but there are some basics that are considered fundamental to the rest of the exam. Fractions, something that you may not actually have to deal with very often in your real life, but totally show up on the GRE. So the main thing here is knowing that when you add or subtract fractions, the guys on the left of my divider down the middle of the room, these guys need a common denominator. It is naughty to just go just adding across. So 3/4 plus 5/6 does not equal 8/10. If you do that, you will get every question wrong because that's not how it works. You need a common denominator, some multiple of both 4 and 6. When in doubt, you can just multiply 4 times 6 and turn this whole thing into 24ths. But if you can choose a smaller number, that's usually better. In this case, 6 and 4 both have 12 as a multiple. So this is really 9/12, because we multiply the numerator and denominator by 3 to turn it into 12ths. And then this one, we multiply the numerator and denominator by the same number, 2, to get 12ths. So this is 10/12ths. So that equals 19/12ths. Sometimes it'll be further reducible at that point, but you can't predict that. 19/12ths are very different from 8/10ths, and that's how wrong you'll be. So, don't do that. Subtraction works the same way. So this would be, using those same numbers, this would be 9/12ths minus 10/12ths, which would equal -1/12. Again, you can't just go across. This is to be contrasted with multiplication and division, which do not require a common denominator. Multiplication, you do multiply across. You can just treat this as 3 times 5 over 4 times 6. So that's 15 over 24. It really is that simple. You just multiply across numerator and denominator. Division, on the other hand, you don't necessarily do that. Well, I mean, you do that. In fact, you do it even more than you would think. If you don't remember how to do division of fractions, you take the second of the two that you're dividing, you invert it, you flip it the other way around, and you multiply the two together. So 3/4 divided by 5/6 is the same thing as 3/4 times 6/5, really. And then you just multiply across. 3 times 6 equals 18. 4 times 5 is 20. That's how you do those. Decimals. The main thing is keeping track of your decimal places. When in doubt, add dummies dummies in the sense of like placeholders. So when you're adding 0.7 and 0.35, you may want to make it 0.70 plus 0.35 to make sure that you keep the 7 lined up with the 3 and not inadvertently make it into like 0.42. It actually needs to be 1.05 rather than, if you did 0.35 plus 0.7, you could get 0.42 because you'd be adding 7 to 35 incorrectly. So line them up, put in dummies to make sure. Subtraction, same thing. 0.70 minus 0.35, and so it ends up being 0.35. It's the same thing as 70 minus 35, but then you have to make sure that the decimal points line up. Multiplication, you have several different options, but basically it doesn't matter which one you put on top. You just have to make sure that you keep track of all the decimal places at the end. 7 times 5, 35, 21, 22, 23, 24. So you get 245, and then you have to account for your 3 decimal places. 1, 2, 3. It's 0.245. Division, you have a couple different ways you can do it. 0.7 divided by 0.35, you could actually represent it as a fraction. And then that might make life a little bit easier. You can then also multiply numerator and denominator by the same thing. Multiply them both by 100 to move the decimal point 2 to the right. And you end up with 700 over 35, and then the answer is 20. You can also just do it as long division. So 0.35 goes in, because everybody loves long division. You can also just punch it into your dang calculator. So, sometimes it's going to be faster to do it in your head or on paper. But 0.7, you have to move the decimal point over 2 for both of them, and it amounts to the same thing. So, anyway, a lot of these are easier with the calculator, but sometimes you will still find yourself doing it out on paper because it's faster than actually typing it in. Okay, 2.3 falls exactly halfway between which two numbers? So we're going to have 2.3 in the middle, and we have to decide, and it's going to have the same amount plus and minus on both sides. So is it the same distance from negative 2.3 and 2.3? Well, this is clearly impossible because it's actually at 2.3, and that's not the same distance from negative 2.3, so it's not A. And then we have negative 2.3. Oh, and we have to determine here, this is negative 4.6 difference. So this is still negative 4.6 difference. On the other side here we have 4.6, which might seem right, but 4.6 is actually only 2.3 more than 2.3. So we had to subtract 4.6 on the left, add 2.3 on the right. It needs to be the same number. Negative 1 and 3. So if we have negative 1 here, to get from 2.3 to negative 1, we need to subtract 2.3 and then subtract another 1 on top of that. So this is minus 3.3. And to get to 3, we just added 0.7. So still not there. Negative 0.5 and 5.1. So to get here, we subtract 2.3 and then another 0.5 on top of that. So this is minus 2.8. To get here, it's very interesting here. You simply add 2.8. 2.8 plus 2.3 equals 5.1. So let's keep these separate. Clearly it is this one. 2.3 is exactly halfway between negative 0.5 and 5.1, even though the two numbers don't look anything alike. We had to correctly add and subtract decimals, though, on both sides to make sure we got it. Ratios and proportions. You basically can't avoid these. Ratios are then the comparison of two numbers which will look like a fraction or a division problem. So 4 to 5 is equal to 4 to 5, and that's equal to, written out, 4 to 5, because it could be written out like that in a word problem. Any of these are interchangeable, and sometimes you can set up, when you're given a word problem involving ratios, you can take the words and convert them into a chart to help keep things a little bit straighter. So for example, if you have 3 sisters split the cost of a plane ticket, if the flight costs $360 and Mary pays twice as much as both Sarah and Pauline, how much did Pauline pay? So we know that Mary paid twice as much as Sarah and Pauline. So Mary equals 2S, Mary equals 2P, and how much did Pauline pay? So it might make it easier to, and this also means that Sarah and Pauline paid the same amount. So we know then that what Sarah paid and what Pauline paid and what Mary paid, that equaled $360. But then we also know, so we're kind of setting this up as a chart here. So we really know that Sarah, well, we want to do it in terms of Pauline because that's what we're doing. Sarah equals Pauline, Pauline equals Pauline, and we know that Mary equals 2 times Pauline. So that ends up equaling 4P equals 360, and P for Pauline's value is 90. So keeping the values straight, you may want to set up a chart initially which keeps things straight, and then if you try to condense things, have it condensed. I'm really unhappy with that P there. That's better. This may help you keep it straight in your head which things represent what. So a proportion, as differentiated from a ratio, is 2 ratios set equal to each other. So it would be something like 1/2 equals 2/4. Now the reason you'll get a proportion is usually because one or more of these numbers is actually missing. It's a variable instead of an actual constant. So you might get something like, if Hal can answer 4 questions in 64 minutes, which we could represent as 4 per 64, 4 questions per 64 minutes, that would equal some other, I probably should make it a capital Q. It will be some other number of questions, X number of questions, in 12 minutes. So now we have 2 ratios that are equal to each other, but we need to figure out what this missing X is. And we can talk about how to do that later on. You actually cross multiply, or just multiply both sides by 12, and then both sides by 64, and then divide by whatever that number is. I don't really need to talk you through it because we'll be doing more practice with this later, but one of the things you can do is just multiply this times this. I'll rewrite it here. So it's really just 4 times 64 equals X over 12. So then you would say, 48 equals 64x, divide both sides by 64, and there's your answer. And you can do that with your calculator. Exponents and square roots. Another thing that you probably haven't dealt with for a very long time, but another one of the things that really you are going to have to commit to memory. I'm sorry, today's really a commit to memory day. Remember, you can do practice questions on Grocket afterwards. So your rules of exponents are as follows. So we have general rules, first off. So first off, anything to the 0 power is always going to be equal to 1, even 0 to the 0 power. So anything to the 0 power is equal to 1, whereas anything to the first power is just equal to itself. 2 to the first power is 2, 100 to the first power is 100, x to the first power is x. Those are relatively easy to remember. We also have rules for adding exponents. If you have, oops, I shouldn't have done that. Let's go back one. So if we have x squared plus x cubed, those are the other words for x to the second power and x to the third power, this just equals x to the second power plus x to the third power. You cannot add these two together to somehow get 2x to the fifth. You don't multiply the things together to get 2x to the sixth or just x to the fifth or anything like that. All of those are naughty. You just have to leave them alone. If they have the same base and different exponents and you're adding them, you leave it. Multiplying them, on the other hand, you don't leave them alone. When you're multiplying 2 exponents of the same base together, you add the exponents. So x to the x squared times x cubed equals x to the 2 plus 3, which equals x to the fifth. If ever you're unsure about this and you're saying, oh, Jim, and the chin stroking is optional, Jim, I don't know about that. I don't think I can remember that. You can always write it out with small enough numbers to kind of re-verify for yourself that this is right. So x squared is x times x, and we're multiplying that times x to the third, which is x times x times x. So that's our x to the third right there. This is our x squared right here. Multiply them the two together, we have 5 x's. That's x to the fifth. Pretty cool. Now, when you raise exponents to exponents, that's when you finally, people have been itching to multiply these exponents for a while, maybe. When you raise an exponent to an exponent, that's when you multiply the two together. So this becomes x to the 2 times 3, which equals x to the 6th. And again, that's another one that you can write out when the numbers are small. So it's x squared cubed. So here's one x squared, here's another x squared, and here's our third x squared. When you multiply all of these together, that's 6 x's. It's x to the 6th power. Finally, dividing them, so x over y to the third power, you aren't really doing the division at this point, but this can be rewritten x to the third times y to the third. So that may end up being helpful in solving a particular problem. And it may be also helpful to go in the opposite direction. So just know that you can do that little conversion. Finally, when you are dividing an exponent by an exponent, you're kind of factoring things out. So you're actually subtracting these exponents from each other. This is x to the 2 minus 3, because you may recall that like x to the negative 2 is 1 over x squared, x to the second power. So x squared over x cubed is x to the 2 minus 3, which is x to the negative 1. And remember, negative powers are not necessarily negative numbers. X to the negative 1 is equal to 1 over x, or 1 over x to the first power. Whoops. All right, so using those rules, putting them into effect here. Remember how I mentioned that dividing by 0 is naughty? When you see problems that say if x does not equal 0, that's probably, if they give you something that x does not equal, they're doing it so that they're not dividing by 0. Note that if x did equal 0, x to the 4th power would still be 0, and we'd have 0 in the denominator, which is naughty. So the GRE and Grocket seek to avoid breaking the laws of time and space by dividing by 0. So we will go out of our way to avoid it. We can, however, follow our other exponent rules here. So first off, we raise these guys to exponents. X squared to the third power, we multiply the exponents. This becomes x to the 6th times x to the 4th times x squared. And you could do one of two things. You could add all of these up and then subtract this, or you could recognize that these two guys vertically, an x to the 4th up here and an x to the 4th down there, will cancel each other out, and we're left with x squared times x to the 6th. When you multiply two exponents of the same base together, you add their exponents, which equals x to the 8th. So this is x to the 6 plus 2. And there we have it, choice D. Finally, your rules of roots, very important. As important, possibly even more important. No, I'd say they're about equally important as the exponent ones, and so something else you should devote to memory. Remember that the square root of something, let's start with this one down here, this will probably be easiest. The cube root of x is equal to x to the 1/3 power. So note that square roots can be converted to regular, like, little number exponents as much as you want, and sometimes that makes life easier. So the square root of something is equal to x to the 1/2 power. All right, so when you square a square root, you basically undo the square root. So the square root of 2 times the square root of 2 just equals 2. The square root of x times the square root of x equals x. On the other hand, if you add them together, you're not undoing the square root, you're just creating more of the square roots. Square root of x plus the square root of x equals 2 times the square root of x, because, hey, look, there's 2 of them. Again, when you multiply roots together, it helps to turn them into those exponents. The cube root of x is equal to x to the 1/3 power, and that's times x to the 4th root of x, which is x to the 1/4 power. And remember, when you have two exponents of the same base, and you're multiplying those exponents together, you add the exponents together. So we need a common denominator. Remember, we covered fractions also. So 1/3 plus 1/4, we need a common denominator. That's going to be 12. So this is 4/12 plus 3/12 equals 7/12. So this is going to equal x to the 7/12. Crazy, huh? Finally, when you raise exponents to exponents, you probably still want to convert them to fractions. So again, this is the 4th root of x, which is x to the 1/4 to the 3rd power. And when you raise exponents to exponents, you multiply them. So this is x to the 1/4 times 3, which equals x to the 3/4. Memorize these, commit them to memory, put them up on next to the bathroom mirror or by your pillow at night so you see it first thing when you wake up in the morning. Until you have these down cold, they really are important for the test. So here's an actual problem. Q is an integer and also the square root of p. Then which of the following is also an integer? So we have Q equals an integer, and we know that Q is the square root of p, so Q times Q equals p. And an integer times an integer is also is always going to be an integer, like 3 times 2, 4 times 5, whatever. As long as both of these are integers, and we already know they are, then we know that p is an integer. So which of the following is also an integer? Indicate all of them. And if you're not sure about this, go ahead and pick numbers. Just say that Q equals 2 and P equals 4. Q is an integer and it's the square root of P. So just pick numbers, and then P over Q. P over Q is 4 over 2, which equals 2 over 1, which is an integer. So there's 1. Q over P, that's 2 over 4, which equals 1/2, which is not an integer. The square root of Q would be the square root of 2. That's not going to work. But the square root of P we already established as Q. We already knew that that was an integer, so D is also definitely an integer. So finally, your strategies for these exponents and square roots, notorious for traps. Just like even just in the difference between raising an exponent to an exponent and multiplying two exponents of the same base, that's the most common one. So watch out for those. When in doubt, try to rederive the rules with simple numbers. Default to what you do know. You can even write it all out this way if you need to, or practice it with real numbers on your calculator. So you do that. Know your calculator ahead of time, so practice things that use the calculator that like it is on the actual test. Positive fractions, this is one of the traps or the exceptions to rules. When you raise a fraction like 1/2 to a higher power, it becomes smaller. $500,000 is a bigger amount of money than half of $500,000, which is a higher power of the fraction 1/2. So note that they get smaller. Note that negative numbers alternate between being positive and negative. If x equals -1, let's just say, x squared is -1 times -1, but negative times negative is positive. X squared equals 1. X cubed equals -1. X to the 4th goes back to being 1 again. So just know that negative numbers behave in funny ways with when they're the base of the exponent. The square root of 4 is 2, not plus or minus 2. So the radical sign here always means the positive square root. Always, always, always on the GRE. On the other hand, like we give here, x squared equals 4. This is x equals 2 or -2, because either one of these squared becomes 4. So just keep track of the difference. And then finally, fractions -0 and 1 to test particular statements relating to exponents. That's a lot to practice, but of course, there's homework. Okay, the old clock on the wall says that's all for GRE Math 1. As I think I alluded to earlier, there is some homework. I mean, I guess I'm not going to come to your house and scold you if you don't do it, but if the whole point of this is to do better on the test, you really should do this. And if possible, do this before the next video in the next, class. Because, aside from practice making perfect, we do build on these concepts as we go. If any of these caused you problems, you can do targeted practice on number properties, arithmetic, decimals, ratios and proportions, and exponents and square roots. We have questions tagged with these same tags, these same phrases. We have our questions in the Grocket database tagged with these. So whichever of these you need practice on, and you should practice all of them to make sure that you are in good shape on all fronts. These tags allow you to do targeted practice. And since these are the fundamentals on which the later stuff is built, I guess I don't want to, beat you over the head with this, but really, please do your homework and, pay attention to it. I personally recommend doing some practice every day. If you even if you don't have time to do a whole bunch, even if you don't have time for an hour and a half, doing 2 problems before bed keeps you from doing the thing where you say, oh, I'll just do it all on the weekend, and then you try to commit to 8 hours of GRE studying at once, and then when you can't do it because the prospect of doing 8 hours of GRE studying drives you mad, then you don't feel guilty. If you study a little bit every day, you'll do much better than if you put it all off and just promise yourself that you'll do twice as much next time. Anyway, targeted practice on these for next time.